Hello friends. So today we are going to do some more questions from the year 2019 mains, and there are total 14 questions from the 2019 mains, and this is the part 2 of these 2019 mains questions. So we start from the first one. It states that a conducting circle loop is made of a thin wire, has area 3.5 into 10 to the power minus 3 meter square and resistance 10 ohm. It is placed perpendicular to a time-dependent magnetic field Bt, which is 0.4 t sine 0.4 pi t. The field is uniform in space. Then the net charge flowing through the loop during t is equal to 0 and t is equal to 10 millisecond is close to. So we are given a circular loop and we have to find out what will be the net charge flowing through the loop between the time. Okay, and here the field is our time dependent field, that is given as 0.4 multiplied by capital T. So in this case we are given a field and we can start from our area of loop is given to us, and first of all we are going to find out the flux, and flux we are going to find out the EMF, and that is going to give us further the current. So we start with the flux, and we know that the magnetic flux, that is our phi, is magnetic field and area A. So magnetic field is given as time dependent, so we can modify this equation as phi of t is equal to magnetic field that is time dependent and area A, and it is given as 0.4, and we have this as sine of 50 pi t. And area is given as 3.5 into 10 to the power minus 3. So multiply by 3.5 into 10 to the power minus 3. So we get this as our flux. Phi of t will be coming equal to, this will be 0.4 into 3.5 into 10 to the power minus 3, and we have this as sine of 50 pi t. Now we can find out the induced EMF. Induced EMF will be equal to minus d phi by dt, and this is also time dependent, so we can write this as induced EMF will be equal to minus d of dt, and we already know the formula for the flux. So this is 0.4 into 3.5 into 10 to the power minus 3, and we have sine of 50 pi t, and this will simple derivative, so we get a EMF E will be equal to, we get this as, the rest of things will be same, so this is 0.4 into 3.5 into 10 to the power minus 3, and then we come this as 50 pi, and cos of 50 pi times t. So therefore we can write that our EMF will be equal to, this will be coming close to as, sorry, minus, this will be our yeah, we can keep it like this only. There is no need to further solve, we can solve it later on also. And now we come to our current, and current is equal to E upon R, and this is our 0.4 into 3.5 into 10 to the minus 3, and this is our 50 pi cos of 50 pi t, and resistance is given to us as 10 ohm. So therefore you can say this 10 goes by this 5, and we can write that our current will be now equal to, we can write this as, this will be 4 into 35 into 500, and this comes at 10 to the minus 3 multiplied by pi, and we have cos of 50 pi t, and we can solve it little bit. We get this is current, and this will be our 20 comes 7, so this will be 700, and divided by 100, 10 to the minus 3 times pi, and cos of 50 pi t. This goes away, so we are left with this as current will be equal to 7 pi into 10 to the minus 3 cos of 50 pi times t. Now we have to find out the charge. So charge, we can write, is our dq is equal to I times dt. So you can say charge, which is our dq, is equal to I times dt, and we have to find out the charge from the time 0 to 10 second. So we can write that total charge q will be equal to integration of 0 10 into 10 to the minus 3, and this comes as I times dt, and we already know our I, so we can say our charge will be equal to, we come this as 7 pi into 10 to the minus 3, and this will be of integration 0 to 10 into 10 to the minus 3, and this is cos of 50 pi t and dt. So we can integrate it. We get q, this will be 7 pi 10 to the minus 3, this comes over 50 pi, and I think I forgot one sign. Yep. Yeah, that's correct. And this comes as sine of upper limit, that is our, this will be our 50 pi into 10 into 10 to the minus 3 minus sine of 0, and we get this as the charge will be approximately equal to 14 millicoulomb. Okay, obviously with the negative side. So this question was quite easy. So that is our, you can say 0.14 millicoulomb. I think, let me check once again. So here pi goes with pi, and we are left with this as q is equal to -7 into 10 to the power -3, and this comes as our sine of, this will be over 500 divided by 1000 pi, and this goes with this. So we are left with q is equal to -7 into 10 to the power -3, and this is our sine of 0.5 times pi. So this will be giving me approximately as -14 millicoulomb. No, it's the correct one. So the option number D is the correct option. Option D is correct. There is slight correction in the question itself. Okay. So this has to be my magnetic field should be actually 0.4, and this will be our sine of 50 pi t. Okay. So this should be the actual magnetic field, not this equation. We come to the next question, and it was also asked the year 2014, and it says that, sorry, 2019 means, and it says that a magnet of total magnetic moment 10 to the power -2 I unit vector is placed in a time varying magnetic field Bi cos omega t, where B is 1 Tesla and omega is 0.125 radian per second. The work done for reversing the direction of the magnetic moment at t is equal to 1 second is. So we have to reverse the direction of the magnetic moment and find out the work done. So here we are going to find out the energy before and after the, you can say, reversing, and after the reversing, and solve it and get the answer. Okay. And we know that the potential energy of a magnetic dipole in a magnetic field, potential energy of a magnetic dipole in a magnetic field it is given as U, and that is equal to minus of magnetic moment and magnetic field, and we have to find out the work done. So we can say work done to change the orientation of the magnetic moment that will be equal to change in the potential energy. This will be equal to change in potential energy. So we can write work done W will be equal to change in potential energy, or we can say final potential energy minus initial potential energy. And we can easily find out the various values, and keep in mind that we have to find out everything at t is equal to 1 second. So you can say that magnetic field at t is equal to 1 second, we are given the equation for that, that is our B of t is equal to bi I unit vector, and we have cos of omega t. Magnetic field is given as 1 Tesla, I unit vector, omega is given to us as 0.125, and time is our 1 second. So this gives us that our magnetic field will be equal to cos of 0.125 I unit vector, and this comes close to 0.992 Tesla. Now we can find out our initial energy. That is, our Ui will be equal to minus m unit vector, and the magnetic field at time 1 second. Magnetic moment we already know is our 10 to the power minus 2, and this is also our I unit vector, and we have this as 0.992, and this is also I unit vector. So we get our initial energy will be approximately equal to minus of 0.00, and this is 992 joules. Now we find out when the magnetic moment is reversed. Magnetic moment is reversed. So this gives us minus of magnetic moment, giving us minus of 10 to the power minus 2 I unit vector. I unit vector. So we find out our final energy. Final energy is minus of the, and we have a magnetic field at time, that is our 1. So this comes a minus, and we get minus of 2, and we have this I unit vector, and this is 0.992, and this is also our I unit vector. So this gives us our final energy will be approximately equal to 0.00922 joules. Now we have to find out the work done, which is our W is equal to UF minus our UI. So we get this as, this is our UI is, yeah. So UF is our 0.00922 minus of minus, and initial energy is 0.00992. So minus minus becomes plus. So we get our work done will be equal to, we can write this as twice into 0.00922. Sorry, let me check. 992, yeah, my mistake. Here it is 9, and here also 9, because only difference will be in their positioning. So we get that our work done will be approximately equal to 0.01984 joules. And the option that is the correct one is our closest, is our, you can say, option number C is the closest one. Option C is correct. We come to the next question. It was also in 2019 mains, and the question states that a hoop and a solid cylinder of same mass and radius are made of a permanent magnetic material with their magnetic moment parallel to their respective axes. But the magnetic moment of hoop is twice of a solid cylinder. They are placed in a uniform magnetic field in such a manner that their magnetic moments make a small angle with the field. If the oscillations periods of hoop and cylinder are Th and Tc respectively, then we have to find out what will be the relationship between their respective time periods. And here it is given that magnetic moment of the hoop is twice through that of the cylinder, and the mass as well as radius of hoop as well as cylinder is same. So we can say that magnetic moment let us suppose we represent it as by m, then magnetic moment for hoop will be equal to twice m, and magnetic moment for the cylinder will be equal to m. And it is also given that their axes are parallel to the magnetic moment. So it mentioned that axes are parallel to magnetic moment, and it says that they are placed in uniform magnetic field making a small angle, and it is also given that they are placed in a uniform magnetic field making a small angle, and because of this they undergo angular oscillations. They undergo angular oscillations. And we know the standard formula for the period for a magnetic moment. We can say oscillation period. We can say that oscillation period for a magnetic dipole that is represented T, and this T is equal to 2 pi square root of I divided by mb, and here this I is the moment of inertia about its axis. I is moment of inertia about its axis. M is the magnetic moment and B is the magnetic field. Okay. So we can reformulate the moment of inertia for hoop as well as cylinder. So we say moment of inertia of hoop, let us call that IH, and that will be equal to our mr square, and moment of inertia of cylinder, let us call that IC, and that will be equal to half mr square. And magnetic moments are already given to us, that is 2m and m. So we can say that magnetic moment for hoop, that is our mh, which is our twice m, and for cylinder let us call that as m of c, and that is equal to m. So therefore we can write their time periods for hoop, which is our th, will be equal to 2 pi, and we substitute the value, we get mr square divided by twice mb, and this comes as m goes with m, and we are left with this 2 pi square root of half, and we have this r square by b. Similarly, we can write for cylinder is equal to 2 pi, moment of inertia is half mr square divided by mb, and here our m and m cancels out, so this gives us 2 pi, and it will be half r square by b. Now we simply find out the ratio. So th by tc will be equal to, we have this is 2 pi square root of half r square by b, and 2 pi square root of half r square by b. Numerator and denominator are same, therefore we get that our time period for the hoop as well as time period of the same cylinder will be same. So option number B is the correct option. Option B is correct. So we come to the next question, and in this question it is said that a moving coil galvanometer has a resistance 50 ohm and it indicates a full deflection of 4 milliampere current. A voltmeter is made using this galvanometer and a 5 kilowatt resistance. The maximum voltage that can be measured using this voltmeter is close to. So we are having a voltmeter, and in this case we are given that it has a resistance of 50 ohm and full deflection current is given as 4 milliampere and is converted into galvanometer and a 4 kilowatt resistance. So we can say the resistance of the galvanometer, that is G, resistance of galvanometer, that of G is given as 50 ohm, and the current through the galvanometer, which is full scale deflection current, through galvanometer, which is our Ig, and that is given as 4 milliampere. So this is 4 into 10 to the power minus 3 amperes. And the resistance of the voltmeter is given as it has to be ohms, not watt. And we are given that resistance of voltmeter that is of R is our 5 kilo ohm. So this is about 5000 ohms. So we can draw a approximate figure for that. So here we have a resistance. So this is our resistance and this is our galvanometer resistance, and in combination it is going to form a voltmeter. And here is our current, that is our Ig. So therefore we can write the equation that our voltmeter is going to measure voltage V, which will be our galvanometer current and galvanometer resistance plus the resistance of the voltmeter. And we know all these values, so we can substitute it. 4 into 10 to the power minus 3, and galvanometer is of 50, this is about 5000, and we get this as V is equal to 4 into 10 to the power minus 3 into this comes as 50, which will be equal to 20.2 volts. So we can say voltage is approximately 20 volt. This is the maximum voltage it can measure. So option number D is the correct one. Option D is correct. We come to the next question, and in the next question it is given that the resistance of galvanometer is 50 ohm and the maximum current which can pass through it is 0.002 ampere. What resistance must be connected to it in order to convert into ammeter of the range 0.5 ampere? It means we have to convert the galvanometer to a ammeter, and for that we have to connect a shunt resistance in parallel to that. So we can draw a approximate figure for that, and if G is the galvanometer and we have to connect a shunt resistance across parallel, so let us this is a shunt resistance S. I is the total current, Ig is the current flowing through a galvanometer, and this will be our I minus Ig. And so here the shunt resistance and galvanometer both are in parallel, so we can say the potential difference across the galvanometer will be same as that of your shunt resistance. So you can say that potential difference across galvanometer should be equal to potential difference across the shunt resistance. Okay. So therefore we can write Ig multiplied with the galvanometer resistance G, and we have this as I minus Ig multiplied by S. Okay. So we can easily reformulate this equation. This gives us that our S will be equal to galvanometer current multiplied by galvanometer resistance and I minus Ig. And we know all these values. We are given this as 0.002 multiplied by 50. Total current is maximum current, that is 0.5, 0.002. So shunt value S will be approximately equal to 0.2 ohms. So we have here option number 0.2. Option number A is correct. Option A is correct. We come to the next question, and here it is given that a bar magnet is demagnetized by inserting it inside a solenoid of length 0.2 meter and 100 turns, carrying a current of 5.2 ampere. The coercivity of the bar magnet is. So we have to find out the coercivity, and coercivity we can indirectly say that we have to find out because we have to demagnetize the bar magnet, so that coercivity will be, you can say, related with the magnetic field that will be produced by the solenoid. So you can say the magnetic field, because of the solenoid, magnetic field of a solenoid, that is our B, is equal to mu naught n times I, where this n is number of turns per unit length. Number of turns per unit length. So we can say this is our number of turns divided by length. And number of turns are given to us 100 and length is 0.2. 100 divided by 0.2, so this comes as 500. So now we can easily, mu naught we know is our 4 pi into 10 to the power minus 7. So we can say our B is equal to 4 pi 10 to the power minus 7 multiplied by 100, and current is our 5/2 amperes. And this will be magnetic field will be approximately equal to 2600 ampere per meter. So this will be our coercivity of the bar magnet. Coercivity of bar magnet. So option number C is the correct option. Option C is correct. We come to the next question, and we are given here that it was asked in the year also in 2019, and it states that at some location on Earth, the horizontal component of Earth's magnetic field is 18 into 10 to the power minus 6 Tesla. At this location, magnetic needle of length 0.12 meter and pole strength of 1.8 ampere meter is suspended from its midpoint using a thread. It makes a 45-degree angle with the horizontal in equilibrium. To keep this needle horizontal, the vertical force that should be applied at one of its ends is. So we are given that there is a needle, and that is making an angle of magnetic needle making angle 45 with the horizontal in equilibrium. And obviously, because of there will be torque produced by the magnetic field, and in order to balance that, we have to find out that torque actually. And we start from the given information. So we are given that the torque, or rather we can say we know the torque due to the magnetic field due to magnetic field, and that is our tau is equal to mbl, and we have sine of theta, and at equilibrium net torque should be equal to 0. At equilibrium net torque is equal to 0. So we have to keep in mind. So first of all, let's find out the effect of the Earth's magnetic field. So we calculate the vertical component of the Earth's magnetic field. Vertical component of Earth's magnetic field, and suppose that is given as BV, and that is nothing but we can see if the angle of dip is theta, then the tangent of theta will be vertical component divided by the horizontal component. Okay. You can say that for angle of dip is our theta, so this gives us that tangent of theta will be our vertical component and the horizontal component, its ratio. Theta is given to us a 45 degree, and so this gives us that tan of 45 is equal to BV upon BH. Tangent of 45 is our 1. So this gives us vertical component is equal to our horizontal component. Therefore, we can write that the vertical component will be equal to 18 × 10⁻⁶ Tesla. Now we come to the torque part, torque due to magnetic field, and let us represent it by tau B. So we say that tau B is equal to m vertical component, and we have this I cos of theta, L cos of theta, sorry, not I, L cos of theta. Okay, and we substitute all the values, we get this as 1.8 into 18 into 10⁻⁶, and we are given this is 0.12, and angle is about 45, that is our cos of 45. So this gives us that our torque due to magnetic field will be 2.72 into 10⁻⁶. Now this is our torque, and the torque to the applied force at one of its end. You can say the torque, because in order to balance this torque generated by the magnetic field, we have to apply a force, and that force is going to generate a torque. So we can say that the torque due to applied force F at one end of the needle let us call that as tau F, then tau F will be equal to the applied force multiplied by L by 2. And for equilibrium, this tau F should be equal to tau B. Say for equilibrium, tau B is equal to tau F. We simply substitute the values. We get F into L by 2, and tau F we calculate 2.72 into 10⁻⁻⁶. So we get this as F will be equal to twice into 2.72 minus 6 divided by length, which is given as 0.12. So this gives us that the applied force will be close to 4.53 into 10⁻⁵ Newton. So the option that is correct one is our, I think this was only required, yeah. (10⁻⁻3). So I think closest option is our option number B. This is the closest one which you can find. You can say option B is the correct one. Is correct. Let me check whether these options are correct or not, or my calculation is wrong. This formula, yeah, sine. Oh, my mistake. I have written a cos here. My mistake. This has to be sine. Sine of theta. Okay. And we have here and I think magnetic moment is my m into L multiplied by B sine of theta. Magnetic moment is 1.8 into this. Magnetic field we found as, this is also correct, and this is our sine of 45. This gives us the torque is, yeah, this one is also correct, L by 2. So this is our, yeah, the answer is correct. I think might be the option might be wrong. Yeah, so the option is wrong. Answer is correct. We come to the next question, and it states that a paramagnetic substance in the form of cube with side 1 centimeter has a magnetic dipole moment of 2 into 10⁻⁻⁶ when a magnetic intensity of 60 into 10⁻³ is applied. Its magnetic susceptibility is. So here we are supposed to find out the magnetic susceptibility, and that is our, you can say, dipole moment, and with respect to our, you can say, we already, I think it is magnetic intensity that is given to us. Okay. So first of all we are going to find out the its intensity of magnetization. Magnetic moment is given, magnetic intensity is given. So yeah, we start from there and we say the intensity of magnetization, the intensity of magnetization, that is our I, let us call this Im, and this will be equal to magnetic moment divided by volume. And magnetic moment we already know is our 2 into 10 to the power minus 6. So this comes as 20 into 10 to the power minus 6, and volume is our side is 1 centimeter cube. So this comes as 10 to the power minus 6. So this gives us as a 20 ampere per meter. So this is our intensity of magnetization. And next we are going to find out our susceptibility. So we know magnetic susceptibility which is representing something like Z, and that is equal to intensity of magnetization divided by H, and here H is our magnetic intensity. You can say that our H is our magnetic intensity. So now it's quite straightforward. We get this as susceptibility is equal to, we just found out this is our 20 and this is our 60 into 10 to the power minus 3. So this gives us it as 3.33 into 10 to the power minus 4. So this is 3.33 into 10 to the power minus 4. Option A is correct. Option A is correct. So we come to the next question, and here it is said that a paramagnetic material has 1028 atoms per meter cube. Its magnetic susceptibility at temperature 350 Kelvin is 2.8 into 10 to the power minus 4. Its susceptibility at 300 Kelvin is. So we are given number of atoms per unit volume, and we are given magnetic susceptibility at temperature, let us suppose T1 is 2.8, and we have to find out at temperature T2, that is our 300 Kelvin. So we are given that number of atoms per unit volume. Number of atoms per unit volume, that is small n, is our, I think it should be 10 to the power 28. 10 to the power 28. 10 to the power 28. And we are given magnetic susceptibility at temperature T1. So we can say magnetic susceptibility at T1, let us call this as Xi1, which will be equal to 2.8 into 10 to the power minus 4, and we have to find out at temperature T2. So in this, for the calculation, we are going to use the Curie's law. Okay. So we can say from Curie's law, we know that our susceptibility is equal to C upon T, where the C is called as a Curie's constant. C is our Curie's constant. And we can write this equation as C is equal to xi1 into T1. So this gives us 2.8 into 10 to the power minus 4, and temperature is our 350 Kelvin. This gives us C is equal to 0.098. So this we are going to use for the second part, where we have supposed to find out the susceptibility, that is our xi2 will be equal to C upon T2. So this is 0.098 and T2 is our 300 Kelvin. So this gives us susceptibility at temperature is our 3.266 into 10 to the power minus 4. So the option is 3.67 into 10 to the power minus 4. That option number D is the correct one. Option D is correct. Next question, and here we are given that a moving coil galvanometer has a coil of 175 turns and area is 1 centimeter square. It uses a torsion band of torsion constant 10 to the minus 6 Newton meter per radian. The coil is placed in a magnetic field B parallel to its plane. The coil deflects by 1 degree for a 1 milliampere current. The value of B is approximately equal to. So here we are going to find out what will be the value of B. And we are given that we can use that there will be two torques acting on this galvanometer, moving coil galvanometer, or in this you can say on the coil of the galvanometer. One will be the torque due to magnetic field, and another one will be the restoring torque, that because of the you can say there is a coil which is trying to restore the torque, and under equilibrium these two torques should be equal to same value. So we can say that torque due to magnetic field that is our tau B, and that will be equal to our NIAB, and we have torque due to, or we can say restoring torque. Restoring torque, that is our tau K, that will be K multiplied by theta, and at equilibrium this tau B should be equal to tau K. Now it's quite easy, we simply substitute the values. We get this as tau B was our NIAB, and that is equal to K multiplied by theta. So from here we get our magnetic field B will be equal to K theta, and we have NIA. And we substitute the values. We can write this as magnetic field B is equal to 10 to the power minus 6, and theta is our pi by 180, and number of turns is our 175, and we have this current is 10⁻⁻3, and we have area is 10⁻⁻4. So this, okay, so this will be giving us 10⁻⁻6 multiplied by pi, and this comes as 180 multiplied by 175 and 10⁻⁻7, and 10⁻⁻7. So magnetic field B will be equal to this is 180, 187 and 7. This comes as 0 and this goes away. So we come as pi upon 3150. So this gives us magnetic field is approximately equal to 10⁻⁻3 Tesla. So option number A is the correct one. Option A is correct. So we come to the next question, and in this question it is said that we have a magnetic compass. A magnetic compass needle oscillates 30 times per minute at a place where dip is 45 degree, 40 times per minute where dip is 30 degree. If B1 and B2 respectively the total magnetic field due to Earth at the two places, then the ratio of B1 and B2 is best given by. Okay. So we have two frequency of oscillations. One is at 45, another one is 30, and angle of dip is also 2. One is 45, another one is 30. Okay. And the frequency of oscillation of magnetic needle, we can write the formula for that. You can say that frequency of oscillation of the magnetic needle, that is our F, is equal to 1 upon 2 pi square root of m BH and divided by I. Here I is the moment of inertia and BH is the horizontal component of the Earth's magnetic field. So we can write our BH is our horizontal component of Earth's magnetic field. And this I is our moment of inertia. And the horizontal component, that is BH, is given as B, that is the total magnetic field, and cos of angle of dip. So we can say that our BH is equal to B and cos of this delta, where this delta is our angle of dip and B is the total magnetic field, and we have to find out this B1 and B2 ratio. So we can divide this formula into two components. Or let me first of all modify the frequency of oscillation. So we can say frequency of oscillation will be equal to 1 upon 2 pi square root of m, and this we can write now B cos of delta divided by I. Now we can divide into two components. Two parts are there. In the first part we can say F1 is equal to 1.2, and we have m B1 cos of delta 1 divided by I, and the second we can write our F2 same but for the second frequency of oscillation, that is our B2 cos of delta 2 divided by I. And we can simply find out their ratio. You can see F1 upon F2 will be equal to, let us square this side, much more easier. So we get this as B1 cos of delta 1 divided by B2 cos of delta 2. And we have to solve it for B1 and B2. So we can say our B1 upon B2 will be equal to F1 square, and this comes as cos of delta 2, and we have our F2 square, and we come it to cos of delta 1, and we know all the respective values. So we substitute it, we get our B1 B2 is equal to, this is our F1 square and cos of 30, and we have F2 square and we have cos of 45. So this comes as 900 divided by 16, and we get this as square root of 3 by 2, and here we have 45, and this is our 1 upon 2. This 0 and 0 goes away, and we can write this, we get this as B1 by B2 will be equal to 9.16 multiplied by square root of 3 and square root of 2. So this gives us B1 upon B2 is approximately 0.688, or we can approximate it to 0.7. So the option that is correct one is option number B is the correct. Option B is correct. Next question, and here we are given a square loop is carrying a steady current I, and the magnitude of magnetic dipole moment is m. If this square loop is changed to a circle loop and it carries the same current, the magnitude of magnetic dipole moment of the circle loop is. So in this case, first of all, we are having a square loop, current is given as I and magnetic moment is given as m. Then it is converted to a circle loop and carry the same current, and we have to find the magnetic dipole moment. So first of all, we have a square loop, and for this square loop current is given as I, and magnetic moment is given as m. Okay. Now this is square loop is reshaped into circle. And in this case, the current remains same. Current is our I, and we have to find out the magnetic dipole moment. The formula we already know is our I and A. So we say magnetic dipole moment that is of M is equal to I A. A is the area. And let us suppose we are using a wire of length L, and from that wire length L we are going to make square as well as we are going to make a circle. Let us say that let length of wire is equal to L. Therefore, for square with each side A, each side as A, therefore we can write our L is equal to 4 times A. That is our parameter. And for area of square will be equal to our A square, and this we can write as our A will be now L upon 4. So this comes L upon 4 and its whole square, giving us L square by 16. So magnetic moment of square, that is our M, is our I L square by 16. And same length is used for the circle. Same length is used for circle. Therefore, we can write use a circle of radius R. Of radius R. Therefore, we can write our L is equal to 2 pi R. From here, our radius is equal to L upon 2 pi. Now we can find out its area. Area of circle, that is our A. Let us call the A circle will be equal to pi R square, and R we just found out, so this comes as pi, and we have here L square upon 4 pi square. This square cancels this pi, so we get this as L square upon 4 pi. So magnetic moment of circle, magnetic moment of circular loop, let us call that as our MC. Current is our same, and area we just found it is our L square by 4 pi. Now we can simply make a comparison that our moment of inertia of square is our I L square upon 16. So let us find out the ratio. You can say that our moment of inertia of circle and moment of inertia of square, and let me write it this as square ms. This gives us I L square 4 pi, and here we have I L square by 16. I L square goes away, and this comes as 16 oblique 4 pi. So this goes by 4. So we are left with, this is our 4 pi. Therefore, moment of inertia for circle will be equal to ms multiplied by 4 pi. Okay, and for the sake of simplicity, we can represent this ms by m. So we can say circle is equal to 4 pi multiplied by m. So the option that is the correct one is our 4m by pi. So option number A is correct. A is correct. We come to the next question, and here it says that we have two magnetic dipoles X and Y are placed in a separation D with their axes perpendicular to each other. The dipole moment of Y is twice that of X. A particle of charge Q is passed through a line through their midpoint P at an angle theta, which is 45 with the horizontal line as shown in figure. What would be the magnitude of force on the particle at that instant? D is much larger than the dimensions of the dipole. So we are given this figure. We have two dipoles X and Y. X is having a dipole moment of m, and Y is twice, that is 2m, and distance between their respective centers is given as d. So this is charged particle which is passing through the midpoint between the two and at an angle theta with respect to the horizontal. Okay. So we have to find out what will be the force acting on this particle at this particular instant. So the magnetic moment for X will be in this direction, whereas for Y it will be in the downward direction. And distance, we can say, will be equal to d by 2 and d by 2 of point P. So this will be also d by 2. Okay. And here magnetic moment will be m, and this will be 2m. So we know that the magnetic field is equal to our mu naught I upon 2 pi r. So we can say that magnetic field given as B will be equal to mu naught I upon 2 pi r, where I is the current and r is the distance. And the force that will be acting, we can write that as F is equal to Q V cross B. Magnetic force will be per FB is equal to Q, and we have this is V cross magnetic field. So we can just write it that our magnetic field FB will be equal to Q VB, and this will be our sine of theta. And for, we can say that the magnetic field with the dipole moment, we can write that as magnetic field with the dipole moment, and dipole moment is represented as mu. So we can write that our magnetic field will be equal to mu naught upon 4 pi, and this comes as 2 mu, and divided by our, we can call this as, let us call this L cube, where this L is our distance of the axis. Distance of the axis. So we can write it with respect to both dipole, the X dipole, and then we can write for the Y dipole. So we can say for X dipole, So with respect to x, the charge q is in the end-on position. Because for x, let me draw it here. So we have this as a x dipole, and the charge is somewhere here. So it is at the end position. So this is our x. So we can write with respect to x, the charge is at end-on position. End-on position. Therefore, the magnetic field will be equal to mu naught, this is 4 pi, and we have 2 mu, and we can write this as our r unit vector, and this will be our r square minus L square and whole square. And we have said that this L is very much smaller than R. Therefore, we can write that our magnetic field will be of mu naught 4 pi. This comes as mu, and now we come it as a R cube. And this R we can replace by it for x by L. Therefore, we can write for x, this will be our mu naught upon 4 pi, and we have this 2 mu, and we call this as a L cube. Similarly, we can, okay, let's first of all find out what is this b of x, because mu is given, so we simply substitute value of mu. So mu is given as m, so this gives us b of x is equal to mu naught 4 pi, and the L will be our distance, that is d by 2. So this comes as 2m divided by whole cube. Okay. And we can say that our L is equal to here d by 2. Similarly, we write for y dipole. And here the charge is on side-on position. Okay. So we have our, this is our y, and it is side-on right at the middle. Okay. So the charge is somewhere here. This is our q. So it is in a side-on position. Okay. We can say with respect to y, the charge is side-on position. Therefore, we can write that our magnetic field will be mu naught 4 pi, magnetic moment we can put capital M, and this will be our r square plus L square, and this comes as 3 by 2. And once again, our L is very much less than R, so this gives us that the magnetic field will be equal to mu naught 4 pi, and this comes as, oh sorry, here it should be mu, and this is our mu upon our L cube. And mu is given as 2m, and our L is equal to d by 2. Therefore, we get for y is our mu naught 4 pi twice m, and this comes as d by 2 whole cube. So if we see that both bx and by are equal, so this gives us that our bx is equal to by, and bx and by will be both perpendicular to each other. Okay. So we can find out there the direction of these two gives us the direction of the magnetic field. Okay. So we say bx and by, let me write this way, bx is perpendicular to by. So we can say the resultant will be the direction of the magnetic field. Therefore, their resultant will be direction of the magnetic field, and we can draw an approximate figure for that also. So we have our bx and by. So one component will be this way and another one this way, of a by, bx, and the resultant will be in this direction. So this is a b, and the velocity of the charged particle is also along the same path. This is a velocity v, and the magnetic force, that is our Fb, is equal to our qvb sine of theta, and here the velocity is parallel to our magnetic field. This gives us that theta is equal to 0, so thus our Fb will be equal to 0. So option number B is the correct one. Option B is correct. We come to the next question, and it states that a coil having n turns and radius r carries a current I. It is held in xz plane in the magnetic field Bi. The torque on the coil due to magnetic field is given as. So here we have to find out what will be the torque, and torque we know is our magnetic moment cross magnetic field. Torque tau is our magnetic moment cross magnetic field, and our magnetic moment that is our m is equal to NIA, where n is the number of turns, I is the current, and area is the area vector. So it is said that the coil lies in xz plane. We are given that coil lies in xz plane. Therefore, the area vector will be area vector A is along, that will be a perpendicular, that is our y axis, or we can say j unit vector. So we can write that our area A is our pi r square, and this we have a j unit vector. So therefore magnetic moment m will be equal to n I pi r square, and we have this as j unit vector, and magnetic field is also given as b into I unit vector. So we can write that our torque tau is our Ni, we have this as pi r square j unit vector, and this we have cross bi, and j cross I is our minus of k. So this gives us a torque is equal to minus Ni, and we have this as pi r square b, and we have k unit vector. So this is our torque on it. So we have this as Ni b, option number B, magnitude is only mentioned, so we can say option number B is the correct one. Option B is correct. Yeah, so I think, yeah, this completes 14 questions. That was our part 2. Part we have already done. In that part 1 we have done close to 12 questions from the year 2019 mains only. Okay, so this completes all the questions. Thank you.